This is part 11 of a series of videos about parametric curves and the associated parametric equations. In the last video or two, we've been experimenting with some code in Mathematica that shows the graph of three related functions in this kind of situation. When you've got a point that moves through the plane as time goes by, both the x and y coordinates of the point are functions of time. X equals f of t, so f is the name of the function describing how x changes. Y equals g of t, so g is the function describing how y changes. There's a conceptual leap that you can make to also say then that the point x comma y is some function of t as well. I call that function c. C is a function that gives you a point out when you plug in a number. Its first coordinate is f of t, its second coordinate is g of t. In this video, we're going to experiment a little bit more with that code, and we're also going to talk more about eliminating the parameter. It's going to be a little abstract. You're going to really want to pay attention, maybe take notes, stop the video, think about what's going on. So here is the situation. We're just going to focus on these equations here. The original functions as defined for straight line motion at a constant speed were these functions here. X equals f of t equals negative 3t plus 2 gives you the x coordinate as a function of time. Y equals g of t equals 4t minus 1 gives you the y coordinate as a function of time. And then we can put these together in the point valued function c of t like this. This models straight line motion at a constant speed. It goes from the point 2 comma negative 1 when time is 0 up to the point negative 1 comma 3 when time is 1. In the last video, we talked theoretically about using another function, replacing the t up here with another function. I picked t squared. I called the function h of t to create a new parameterization of the same line segment, but one that's not at a constant speed. I think one thing I'd like to do here in this video is emphasize that this is a new function by giving it a new name. Call it c sub 1 of t perhaps. I'm using the original c of t to create this new function c1. c1 of t is defined by plugging in t squared into c, which again effectively means plugging in t squared into f and g, which would result in the following expression right there. So this expression, x comma y equals negative 3t squared plus 2 comma 4t squared minus 1 is this new parameterization of the same line segment, yet not at a constant speed. In the last video, I also talked about then eliminating the parameter in this situation. Listen carefully. How do you get rid of the t? How do you see that it still is parameterizing the same line? What you can do is take the fact that x equals negative 3t squared plus 2, solve that, that's what I have right here, solve that for t squared in terms of x, and you don't have to bother solving for t itself. Solve for t squared in terms of x like this. Then take the fact that y equals this, y equals 4t squared minus 1, and replace the t squared right there with what it equals in terms of x, right here. Y equals this. I replaced the t squared that was up here with this expression right there. You simplify and you see that y depends in a linear way on x. We are parameterizing the same line. It still starts at the same point at time 0 and ends at the same point at time 1 and still goes in the same direction because t squared still increases from 0 to 1 as t itself increases from 0 to 1. What if we didn't specify what h was? What if I just said I have an h of t, and I'm not going to say what it is? I'm not even going to say for sure that it definitely increases from 0 to 1 as t goes from 0 to 1. It might do something different. It might even increase and decrease. Would we still be parameterizing the same line? Will it still parameterize the line at all? What's the equation of the curve it would parameterize? I claim it'll still be the same line. It could start at a different point and end at a different point, and the interval of time that I'm plotting it over might be different. I could choose something different. It might go in one direction or the other. It might go at varying speeds, but it still will parameterize the same line. That's what I claim. Just to give it a different name, I'll call it C sub 2 of t. And I'm just going to replace all the t squareds with h of t's, like this, this, and this. Of course, which also means I need to do it over here too. Okay, so when you look at this equation, you need to think abstractly. I'm not saying what h of t is, but I'm saying I'm creating a new parameterization of some curve by essentially using this formula. I'm creating a new function c sub 2 of t to be c of h of t, the composition. First, use h of t, plug t into h, then take that number and plug it into c, the original c, back up here. The key thing is we still have a linear relationship between x and h of t and y and h of t. Not x and y with t itself, but with h of t. It's a linear relationship. X does still equal -3 h of t plus 2. It's still linear in h of t, so to speak, even though h of t might be nonlinear. Y still equals something that's linear in h of t as well, 4 times h of t minus 1. And just like I did up here, I can take the fact that x equals -3 h of t plus 2, like I have written here, and solve it for h of t. Okay, I got to replace the t squareds with h of t's again. Just the same way I solved for t squared before. And again, you're not worried about solving for t itself. Just solve for h of t. Then use the fact that y in this new situation equals 4h of t minus 1. Replace the h of t with x minus 2 all over -3, just like I'm doing here. Simplify, and once again you get the exact same line. Again, it might start at a different place, end at a different place, go a different direction, go different speeds, but it's still along the same line. Let's emphasize that to end this video with some particular examples. So back up here I used h of t equals t squared. Let's use the grid that we made in the last video and some other values, some other formulas for h of t to illustrate some new concepts. I'm actually going to go back to a linear h of t, but it's not going to be just a plain t. In this first example, it's going to be a 2t. Maybe you should think about what you think is going to happen here. Really, I'm plotting c of 2t. I'm replacing the t's with 2t's here. It's still going to be linear. X and y will still be linear functions. These graphs in the upper right and the lower left are still going to be straight lines. What's going to happen? Look at that. It seems to be going too far. In fact, let me b go to 1. I made a change. Let's go back to what it was. It's still going too far. See that? What happened there? It's covering the same amount of ground in half the time. If you let t go out to 0.5, notice instead of going out to 1, we start at 2, -1 and end at -1, 3. We're still parameterizing the same line like we should be, twice as fast. Replacing t with 2t makes it go twice as fast. These graphs in the upper right and lower left are twice as steep in absolute value than they would be if we were just using a t. Let's actually go back to a t here. This was the original parameterization of the line segment at a constant speed. Maybe it's a little hard to tell, but these graphs in the upper right and lower left are not as steep as they were a minute ago. Again, you got to look at this graph in the lower left with your head turned to the right at a 90-degree angle to think of it as a function graph in the normal way. What if we replace t with 4t? h of t equals 4t. I hope you can guess pretty quickly that you're going to trace it 4 times as fast. We would trace the entire curve from 0 to 0.25. These graphs here and here are definitely steeper. Okay? If we went the other way and used a small number in front of t, like 0.25, and this is where I want to go back to 4, that's going to go 4 times slower than the original parametrization. And these graphs have a slope that's 4 times smaller in absolute value than the original graphs were with a t there. I would encourage you to, again, use Mathematica if you've got it on your own to experiment with this and think about it some more, but I'll end the video now.